Welcome to day one. If you could have out something to write with and your calculator. We're also going to need our white notes packets out. We'll be in there today. In our planners, we can be writing day one. And we also have on day 4 the tying it all together packet due as well. So today we're going to look at log functions and we're going to build up to derivatives of it. So that equation right there, it's read as log base A of x. And another way you could write that equation by switching it to exponential form could be a to the y is equal to x. So the next one we would read as log base 10 of x. When there's no base written, it's implied that it is 10. And you could write that in exponential form as 10 to the y equals x. And then our natural log is really log base e. Where e is our number e, 2.718 and change. And you could write that in exponential form as e to the y equals x. So why does e equal 2.718? So the value of e is actually based off of a limit. Now, if we go back to pre-calc, you looked at your accrued interest formulas. You had p times 1 plus r over n to the nt. Where r was your rate, p was your principal, t was your time in years, and n was the number of compounds. You also looked at your compounded continuously formula, which was p times e to the rt. Well, something you should have done in pre-calc, and it should be almost a year to the day. I know that the pre-calc honors class talked about this a couple days ago, that you look at when n gets bigger and bigger and bigger. So you compounded it daily, you compounded it yearly, semi-annually, quarterly, monthly, daily, and you saw that this was getting closer and closer to e, and that's what led to the continuously equation. Well, really what's happening from that is these two options for the limits. So let's say we had the limit as x approaches 1. We got 1 plus x raised to the 1 over x. Well, another way you could write that is the limit on the right. Because essentially here, when x goes to 0, this is becoming tiny. And this here is also becoming tiny. So that fraction is becoming huge. Because if you divide by a tiny thing like 1 over 1,000, 1 over 1,000,000, when you do keep change flip, that exponent becomes huge. Well, another way you can write it is x approaches infinity. As x approaches infinity, this spot here, the whole fraction, becomes tiny. But this exponent becomes huge. So these are two different ways of writing the same thing, 1 plus a tiny raised to a huge as x approaches our value. Well, I'm going to go over to the calculator now. And I've already put in, this is that first one there, 1 plus x to the 1 over x. And what I did is I picked values getting closer and closer to 0. Well, notice it does approach 2.718. And then what I did is I put in that second one, 1 plus 1 over x, all the x, and I picked x values that got larger and larger positives. And notice that's also approaching that 2.718, which is e. So in both cases, they are approaching e. So e just comes from these limits. So the big idea that you want to know is e is really 1 plus a tiny to a huge. As that tiny gets smaller and smaller, the huge is this reciprocal of it. And the relationship that ends up occurring is that value altogether ends up approaching our 2.718, or in other words, E. And that's where E is coming from. So on the bottom of the second page, Mrs. Flannery and I often go to this summer math teacher workshop at RIT. And there's this one professor there that has stated several times, people at the workshop have asked him, what do you want your students to know when they come in to college level math? And the thing that he always states is he wants his students to be able to speak graph. Now what's meant by that is, if he says ln of x, he wants his students to automatically have in their head a visual of some key things about that graph. Same thing for other types of functions that are common, like e to the x, sine x, cos x, things like that. He wants the students to be able to jump right to knowing what that graph looks like. So natural log of x. So some key things about natural log of x. Any log function without shifts is going to go through 1, 0. So natural log of x ends up kind of looking like that. So our graph gets closer and closer to the y-axis but never hits it. So therefore our domain is x is greater than 0. And you saw that last year that the inside of your log always had to be positive. Now our range, we go down forever and we go up forever. So our range is just all real numbers. 2 key points that it is good to note on natural log of x. You're always going to have the point 1, 0. And that's because natural log of 1 is equal to 0. And in reality, any log of 1 will be equal to 0, because when you switch it to exponential, anything raised to the 0 is 1. And then the other point is e comma 1, and then that's because natural log of e is just 1. Whenever your base matches the inside of your log, that's always going to be 1, because your base raised to 1 should be the same as that base if you switched it to exponential. So those are the key things we would want you to know about the graph of natural log of x. So going to the next page, we've got, let's see, 5 here. We're going to pause the video for, we'll give you 2 minutes. We'll pause it for 2 minutes, see if you can do those 5. So for the first one, we should have gotten 2. So one of the ways you can think about that is our exponents swing out front with logs. This is 2 times natural log of e, and we just saw that natural log of e is 1, so 2 times 1 is 2. Similar idea, this is e raised to the 1/3, so the 1/3 will swing out front. We'll have natural log of e, so this is just 1/3 times 1. So we should have gotten 1/3 for this one. We just talked about a second ago that natural log of 1 is 0. And we said the domain of natural log is x is greater than 0. So neither of these exist. So you could either say DNE or you could say undefined. That's fine too. Moving down to the bottom, just a quick review of some of our log laws. If you multiply inside the log, that splits up into addition. If you divide inside the log, that splits up into separate logs that are subtracted. The numerator gets a positive log, the denominator gets a negative log. And then any exponents can swing out front. So we want to apply those here, and then anything that's a natural log of a can be rewritten with a p, and anything natural log of b with a q. So our answer should be things in terms of p's and q's, and maybe we'll have constants. So this one we could first rewrite as natural log of a squared plus natural log of b squared because of the multiplication. Swing your exponents out front, and this will be 2 natural log of a. Oops, this should be a 3 here. I miswrote that. That should be b cubed. And then we'll have 3 natural log of b. Well, now if we replace the natural log of a with p and the natural log of b with q, we'll just have 2p plus 3q. And that would be it in terms of p and q. For the next one, first I'm going to write this as natural log. This is going to be e to the 1/4 over a squared, when we take the fourth root of the a to the eighth. When you're dividing, anything in the numerator gets a positive log, anything in the denominator gets its own negative log. But like we saw above, natural log of e to the fourth is going to end up just as 1/4. And we'll have minus 2 natural log of a. So in terms of p's and q's, this will just be a fourth minus 2p. Now there's two ways we can do number 3. The first way is we could do subtraction. So this is natural log of 1 minus natural log of b to the 7th. We can swing the 7 out front. Natural log of 1 is just 0. So we have 0 minus 7 natural log of b. So this becomes negative 7q in terms of p's and q's. So that's one way to do it. The easier way, though, I think, is to rewrite this as b to the negative 7 on the inside. So then you can swing the negative 7 out front, and this just becomes negative 7q. Going to the next page, something else you saw last year was solving log equations. If everything had a log, you wanted to get one log on each side, and then set the insides equal to each other. So we can bring these exponents back up. This will be natural log of 4 cubed, which is just 64, minus natural log of x squared equals natural log of 8. This now becomes natural log of 64 over x squared equals natural log of 8. Well, now because you have one natural log on each side, we can set the insides equal to each other. 64 over x squared is equal to 8. If we cross multiply, we'll get 8x squared is equal to 64. Divide both sides by 8. I'm going to move it up here. We'll have x squared is 8. Take the square root of both sides, remembering your plus minus. Square root of 8 is really 2 square root of 2. But when we check, we need to always have positives inside our log. So we'll reject the negative, and our only answer would be the positive 2 square root of 2. All right, moving down to the bottom, natural log of x can actually be defined as an accumulation function. Natural log can be defined as the accumulated area from 1 to x of 1 over t dt. Now that's true as long as x is greater than 0, and the reason it has to be x is greater than 0 is that's what our domain is of natural log of x. So that seems kind of an amazing fact. How can natural log of x equal that, an accumulation function? We just learned about accumulation functions last unit. How can that be true? Well, let's compare it some. So let's see when x is 4. So we'll do natural log of 4, and we'll do the integral from 1 to 4 of 1 over t dt. And we can just look at that in the calculator, and I've got those two here. There's natural log of 4, and there's the integral from 1 to 4 of 1 over t dt. So notice that accumulation function does equal natural log of 4. So it appears that that one checks out. If we try some others, let's try when x is a half. Because 4 was going to the right for our accumulation function, what about when we go back to the left? Would that still work? So here's natural log of a half, and our integral from 1 to a half. Notice that ended up negative, and we know that really what would happen is you could flip the integral to be 1/2 to 1, and that negates things. So that's why we're getting that negative there. But notice those checked out the same. And then if we go to the next one, integral from 1 to 1, well, we shouldn't even have to put that one in the calculator. Any integral where the bounds are the same, that's 0, and we've seen that natural log of 1 is 0. So it seems by checking a few of them that it does appear to be true. So what we're going to do now on the next page is we're going to look and see what's the slope of natural log's graph at a bunch of different x values. So if you go to a graphs page and type in natural log of x, and then we want to go menu, analyze graph, and then we want to select dy over dx so that we could find the derivative. And then it'll ask us for the position. So you can just type in 1/2 and hit enter, and it should come back with 2. And then we want to do menu, analyze graph, dy over dx again. It'll ask us for the position. Type in 1, and it should give us 1. Let's do it again. Menu, analyze graph, dy over dx. Position, we'll type in 2. It's going to tell us 0.5, but let's put that in as a fraction, so we'll have a half. And here's the next couple as well. So I already did 3, and we got 0.333, so 1/3. 0.25, you got 1/4. So this was 1/3, this one was 1/4. So hopefully you can make a prediction now at 5. What is the slope probably going to be? Well, it's going to be 1/5. So let's see if we can come up with a conclusion. If we want to do our derivative of natural log of x, well, we said natural log of x is the same as this accumulation function. So we should be able to just take the derivative of that accumulation function, and that will tell us the derivative of natural log of x. Well, we saw last unit with one of our fundamental theorems of calculus, if we want to take the derivative of this, we're just subbing in that algebraic expression on top for t, and then you're doing times the derivative of what you subbed in, which in this case, we'd just be doing times 1. So for our derivative, we're just going to get 1/x. So, derivative natural log of x, that's a new rule we have now. It's just 1/x. So in our domain of natural log of x, which was x greater than 0, notice that its derivative, 1/x, is always going to be positive. Well, anytime you have a positive derivative, that tells us the original function is increasing. So that's consistent with what we see from the natural log graph. It's always increasing, so the derivative should always be positive. Let's do our second derivative. Well, y prime, or in other words, our dy over dx, we can think of as x to the negative 1. So our second derivative would be negative 1 x to the negative 2, or in other words, negative 1 over x squared. When you sub in x's, that's because it's a negative 1 on top and a squared on the bottom, it'll always be negative. Well, turn to your neighbor and tell them if a second derivative is negative, what do we know is true about our original graph? Hopefully you told them that it is concave down. So that explains why natural log's graph is always concave down. All right, with the time left in the period, you have two options. You can either work on the tying it all together packet, or you can work on day 1 homework. There's textbooks on the bookshelf behind my desk. Just make sure to stick them back when you're done. There's not enough for everyone, so if there's too many people that want to work on the textbook homework, just make sure to share the books or take pictures and pass it on. But you can work on one of those two things for the remainder of the period.